Hello everyone, welcome back to my tutorial. In this tutorial, we'll solve a elliptic bar by applying torque. This is the elliptic bar side view. So here we are going to apply torque. So this is our analytical calculation. Why we are applying like this is in solid element it has only a 3 translation degree of freedom. If you want to apply a torque or a rotation, so we have to make one point or extra node and make a connection to the surface nodes. That connection is a rigid connection, we need to make it. So now the node having rotational degree of freedom, then we can apply a torque or rotation, everything in this node. To apply the torque, we need to make small correction. So first what we want to do, we just want to create one node. Then we need to make a separate group called group MA a load. I'm just giving a name as load. So this is to apply the material property and sections. Then after creating, so the particular node, that node we need to define as distr, that means discrete element. So similarly, if you have a 3D element, we are used to define a 3D mechanic. Similarly, for point node, we need to define what type of element, that is discrete element. For discrete element, we need to define element property. So the element property is KT or DN. What it means, that it is to defining the stiffness. So K means stiffness. Similarly, by MT or DN is there. Here we need to define KT or DN. K means stiffness, TR means translate and rotate, D means diagonal matrix, and N means node values. So here this is the value we are giving, that this is 0.1. we can give 1. If you increase that, the stress will increase because the stiffness is getting increasing. So stiffness of the rigid element. Then so how we are specifying this rigid element, so this is to give the stiffness to the node. Then we need to give a connection, so to the surface nodes. Just go here there is a surface nodes and there is a point node. We need to apply rigid connection between these two. So for that we need to create a group, so to the surface node and to including this point node, the surface node including this point node, we need to create a separate group that is called, any name we can give. I just given rigid underscore connect CON. So for that we need to apply a rigid connection, that name is called liaison solid, that is solid connection. So this is the way we are going to apply. Remaining things are common. So now we will solve this elliptical bar to applying the torque using Salome meca. So now go to Salome meca. Salome meca is the wonderful pre and post processing software for finite element analysis, and it has the code aster as the solver to solve the finite element problems. So now we'll go for geometry. To simplify the case and to reduce the video time, I have created the geometry. Now I will import the geometry. So I have created the geometry and saved in step file. This is my step file. I will open the step file. So just go to file, import. There is an option called STP. Just click it here. Just go to the location, pictures, code aster, so torsion and elliptic bar, and select this file. Just click OK. Now it will ask me to consider it. Yes. So whenever you import any geometry into the Salome meca or Salome geometry module, check any one of the line or total geometry dimension. So now just go to the model. My maximum length is 1 meter. Just have a look, 1 meter. So now we'll check this dimension. Just go here. So inspection, dimension, there is an option called bounding box. So it will create a box. You just see in Z direction the maximum length is 1, in Y direction it is around 50, and X direction 100. So just go here, is 100, 50, 1 meter. Now all the dimensions are in meter. Now it is correct because I am going to use a unit is meter. So now keep this file. Now we'll create groups to apply the boundary condition loads. Now go for create group. First we'll create a volume group. All. This is elliptic bar. I'm just giving bar. Just apply it. Now just go for face group. The left side face I'm going to fix it. Just select this face. Add. Name it as fix. Just apply. Now the right side face I'm going to I'm not going to apply any load. I'm just naming as master. Just apply it. So because I'm going to create one more node here, for that I just want the nodes in this place. I'm just giving simply just master. Any name we can give it. For sake of it I'm giving master. Now I will save this file. Go for file, save as. So elliptic bar I'm just saving here. I have saved it. Now we'll go for meshing. Select this pad, mesh, create mesh. In this tutorial I'm going to create net mesh, NetGen 1D, 2D, 3D, simple parameter, local length. I'm going, whatever the value it's default it shows, I'm going to divide by 10, 0.01, say OK and play it close. Now just right click it, compute it. Now see, this is a tetra element I have created. This element is enough for my model, this element size. Now just go here, go here, go here. Now you see the node group. We'll check the node group. First one is fix. This is the fixed node group. Now it is correct. Now it is coming as a face groups, no issue. Now this is a master and this is the volume group. Now as you know, we cannot apply a rotational force or rotation to this solid element because the solid element doesn't have any rotational degree of freedom. For that we need to create one more node here. For then we need to create a rigid connection between this surface node to the point load. First we'll create one point load. Go for modification, add node. So we'll check the direction in here. This is X actually, and this one is Y. Then this direction is Z. So this direction is Z. Here you can see. So that Z direction we just want to create node somewhere away from the surface node. So the total length is 1 meter. I'm just giving 1.2. Just see. So we can reduce this 1.1. Yeah, so this distance is enough. I'm just giving 1.1 the center because this is located at the center, so I'm just giving center because it has to be created at the center. So this is enough. Just apply and close. Now we have created the group. Now we have created the node. Now we'll create a group. Go for mesh, create group. Now enable manual selection. It has to be a node group, standalone group. Select this particular node, just add it, make this group as load. just apply it, close. Now see, we have created this load group. Now just go to mesh, compute. Now we have included this node group. Then one more group we want to create, that is rigid connection group. Just go here. So we have to include this point load as well as the surface load. Point load as well as surface load. We have to create a group name called, any name we can give. I'm going to use rigid con to apply the solid connection. So go here. Now we will hide this total mesh, this mesh also, this mesh also. Now we will go for master and particular node. Only this node group I want to create. So go to mesh, create mesh, choose this total mesh. I'll just select this mesh one, mesh, create group. Now enable manual selection, only select this node groups. This has to be node, only select this node group, add it, name this as rigid underscore con to apply the solid connection. Just apply and close. Now as you see, it will show some icon here. Just select this mesh one, go to mesh, compute mesh. Now it will go. Now just close it. Now we are done meshing part. Now we will go for applying the setup. Just go to aster study, stable, just OK, add stage. So now we'll add one by one. First go to read mesh. So we have the mesh one, I'm reading it as MID format. Just apply it, save OK. Now we have read the mesh. Then what we want to do is we need to create mesh, that is group MA, to apply the material property for point load. So use create POI1. So this is I have mentioned here in PPT. So this is to apply the material property section, everything. So assign the model and material property. So for that we have to do this one. So create mileage, create POI, just click it here, go to add. There is two options here, one is node, another one is this one. So we have to give, just cancel. So here there is option called mesh, just read this mesh. So before going into that, we have to read here, read the old mesh. Then you just go here, edit, group of node, edit. There is option called load. Choose this load, point load, save OK. Norm group MA, edit. Here the load will not show. We have to manual selection, we have to do it. Just load, save OK, and save OK. Now we have done. This is named as mesh 0. So you just remember this mesh 0, because after every step we have to use this mesh 0 only. Just apply it, save OK. Now we have done the reading the mesh. Go for model definition, assign final element model, go to edit. So group element, we have 3D bar, just select this one, mechanic, here 3D, just save OK. Now see, we have to read mesh 0, not the mesh 0. Now one more we have to define, that is group of element, edit. Here it will not show because the load it will not show. So we have to name it ourselves, load. OK, that is mechanic. This is not 3D actually, that point load is a discrete node. So we have to choose it from here as discrete. So that is distr. Yes, distr. So just see it here, PPT again. So that is discrete, that is distr, they will call it. So go here, distr, save OK. So remaining thing keep it same, just apply it, save OK. Now we have defined the model. For the point load we need to define the element property. Just go for element property. This is actually discrete. Before, just scroll down here, this model, so nothing is there, just go edit. Now there is an option called Kara, just use this Kara. Here we have to choose KT or DN, this one. Now you see there are two more options is enabled here. First one is group of element. Here the load will not come, we have to name it manually, that is to load. Here 6 property we have to define, so I'm just defining point 1, point 1, point 1, point 1, this to be point 1, point 1, stiffness, everything. So I have defined 6 values, then save OK. Remaining thing you keep it same, just apply it, just have a look here, this is correct only, just say OK. Now we have defined the element property also. Now we'll go for material, just go for define material. So whatever the material we are defining to the solid element, same material we are going to assign it to the point element also. Linear isotropic material. So Young's modulus is 210 e power 9 gigapascal, Poisson ratio is 0.3. Save OK. Just apply it, this is the material we are going to use, save OK. Now we have defined, we are going to assign it. Now go to assign a material. So mesh is, we have to use mesh 0, I have already told that. So this lattice mesh only we have to use. Go to mesh 0, model, single model. Now we'll go for assigning it, edit. So everywhere we have to use everywhere material, save OK, just apply it. So we are applying the material to all, save OK. Now this is we have done. Now we'll go for function. So we are not going to use any functions here, just leave this option, go for boundary conditions, go assign mechanical load. First one is left side, I just want to fix it, enforce degree of freedom. Just scroll down here, there are different properties, model, everything is there. So enforce degree of freedom, plus button, edit. So first we can use blockage also. To easy understanding to the viewers, I'm going to use separately. So group of element node, because I have a fixed group here, that is element group. Edit, fix, see here, this particular group is selected, this is the fix. Say OK. I'm going to fix it in only 3 direction, because this is not required, because solid element doesn't have rotational degree of freedom. So I have fixed it, say OK. Now I have fixed it here. Then what I want to do is, I want to apply rigid connection between this surface node to the point load. For that you just scroll down here, there is an option called liaison solid. Select this one, go here, edit. So here we have to choose group nodes, because we have a group of nodes. Edit, rigid connection, click this one, see. So this surface node as well as this point load, just say OK. Remaining thing need not to touch anything, just say OK. Now we have applied rigid connection. Then finally what we want to do is, we have applied rigid connections, we have fixed it here, we have applied rigid connection here, this point load property also we have defined. Then finally we need to apply torque of 1000 Newton meter. Here you see torque of 1000 Newton meter we have to apply to the point load. Now just scroll down here, there is an option called force node, just tick this one, go to plus, add it, edit, group of node, edit, there is an option called node group. Choose this node, say OK. We need to rotate it. So this is Z direction, we have to rotate it about the Z direction. M is at 1000. Say OK. So it will rotate like this. So now everything we have defined, we can go for apply. So we can check it here. We are fixing the 3 directional dx, dy, dz here, and we are applying moment of 1000 Newton meter, and we are given rigid connection to the rigid con group. So everything we have defined. Now say OK. Now we have done. Now we have to define the analysis. We just go to analysis, static mechanical analysis, material, structural element, model. Here there is third option, load. Just tick this load, edit, choose this load, say OK, just apply it. Now this is the load it will take and it will solve. Then say OK. Now solver we have defined. Meca static is our solver. Finally it will calculate only the displacement, that is the primary variable. We need to view the stress, sigma xx, sigma yy, directional stresses as well as principal stresses, von Mises stresses, everything. For that we need to go for post processing, called champ. Same name I'm going to use, wrestling. Here constraint, here choose sigma element and sigma node. This is the directional stresses it will calculate. There is option called criteria. It will calculate equivalent LNO and equivalent node. Equivalent LNO and node, it will calculate von Mises stresses, stress cost stresses and principal stresses, everything. This is element, this is for element, this is for node. Similarly we can calculate reaction force also. As of now I'm not going to check with the reaction force. So remaining thing we keep it. Scroll down here. Here model, material, structural. Here choose wrestling. Now everything is okay. Now say apply it, say OK. Now post processing also we have done. Now we just go for output. We have to save the results to view the results in paraview. Now just click it here, just go to the location where you want to save. This is my folder. I'm just naming as result.rmad. Save. Then you just click it, this plus button, edit. We need to choose mesh system, mesh 0, and there is a result, that is you have to use calchamp, because the calchamp is the tool. It is calculating stresses and principal stress, von Mises stress, everything from the solver. Go for structural element property, and here in norm champ we can define one by one also. Instead we can go for tau champ. By making S, it will save all the results whatever it's calculating from calchamp. So I just making S. Scroll down here. This is enough. Just say OK. Make it MED format. Just apply it. Save OK. Now see, there is no red color it's showing. That means that we have created, set up everything correct. Now we can go for solving. So just go for history view. Now just click this plus button and click this keep results. Now we'll save this file. Before running it, we have to save this file. Now we can go for 5 seconds. So whatever the message file, it will refresh every 5 seconds. It will show. If any error comes, it will show while running itself. For that, I'm just keeping into 5 seconds. Just go for run. This window for graph, and here we will see the message file. Now it started reading, so the command file. Now see it has solved without any error, and we can view this message file also. If you want to separately view, we can choose it here and we can view. Here itself we can view. Now it has solved nicely and it saved the results with alarm. So we can ignore this alarm, this is simple alarm only. So now we will view the results in paraview. Just go here, use paraview. Now right click in built-in, open, go to pictures, code aster, elliptic bar. Our result file is result.rmd. Say OK. Now we have to choose any one of the displacement I want to see. Just tick this displacement, just apply it. Go here, choose the displacement. So this is the displacement value. This is actually a displacement magnitude. I'm applying a rotation, that means I'm applying torque in Z direction. So I will see the rotation about Z. So see, the maximum rotation is this one, 3.7 into 10 power minus 4. So this value we can check with our analytical value. So just go to the PPT. Here you just see the theta value is 0.000394. So we can check with the here also. It's coming around 0.00037. It's very close to the value. So if you want to see the value here itself, also we can check it. See, this is the maximum value coming in the point only. So to view that value, just go edit, view, Windows. There is an option called selection display inspector. You just make sure this is ticked. Then you just go here. There is a selection display inspector. Just click it here. Just tick this one. Now just go here and make a selection. See, the value is 0.00371 is the value it's coming in code aster. In analytical we are getting 0.00394. It's very closer value we are getting. Now similarly we can check the stress. For that, just go for sigma, just apply it. Just go here, choose the resilient one. I'm just giving fit screen. This is showing magnitude, but I want to see sigma xz. Sigma xz. So there are different sigma xx. This value will come very less only. So only sigma xz will get maximum, because we are calculating analytically as shear stress. Shear stress maximum is coming in. So there are three shear stresses. These are directional stresses: sigma xx, x direction stress, y direction stress, z direction normal stresses. These three are shear stresses. In 3 you just see sigma xy is 2.8, 2. So this is 2.8 e power 5. Xz is 2.5 e power 6, and this one is 1.7 e power 6. The maximum is coming in sigma xz. So this is the value. Just go here, click this one, make this rainbow, apply and close. Now here just go make it 12, just apply it. Now you see the results. Maximum shear stress is 2.5 e power 6, that means 2.5 megapascal. Now here also you can check. Here also we are getting 2.5465 megapascal. So almost closer value we are getting. So in this tutorial we have learned how to apply rigid connection and how to apply torque for the solid object. So, and we have compared the analytical results with the finite element results. So thank you for watching my videos. Please subscribe my channel for more videos. It will encourage me to put more videos in channel, and thank you.